Now that we have started with graphs, I want to spend a little time before we go any further to describe the type of package that you could use to deal with graphs in R. And I'll just point out that there are a variety of packages that you could use. This is just one of them. I find it is a very good package. I'll explain why in a second. What I recommend, but again, I mean, you might find other mechanisms. What I do recommend is to use igraph. igraph, one of the very interesting features is that it is a package that exists also in C and in Python. There's even a Mathematica interface to igraph. So one of the cool things is if you learn how to use igraph in R, well, you can port this knowledge to Python, for example, and it will be just the same. igraph also has very good online documentation, or very good, I wouldn't go all that way. It has a very decent online documentation for an R package, because these things are sometimes a little complicated. And here, no, there's a proper website that is made for this. And it has many, many, many features. It's a very exhaustive package. So a lot of what we will do, you can find there by not just looking at the help, searching for help, etc. So to install igraph, you would just go install packages igraph. I've done that already, so it is already in my library. Then you load the library by just library igraph. I'll make this disappear. As I said, you can find some information by going to their website, etc. So what I want to do today is very briefly, I'm mindful of time, to show you the basic usage of igraph. And that's going to be, how do you set up a graph? That would be the first step. And as I was saying, this is quite a comprehensive package. And so there's a lot of ways to create graphs. And so here what I've done is I've cut and paste from the main help page the functions that you can use to create a graph. And as you can see, there's really quite a long list. And I'll go over some of those functions very quickly. The aim is not to give you a sense of everything that is there, but more so that you see that many things are possible. So there's several ways to create a graph in igraph. So one of them is to use what I would call the usual type of specification. So for instance, this is one that we will use in a second. Create a graph from the adjacency matrix of that graph. You can use adjacency lists, graph atlas. I mean, there's a lot of different ways to create graphs like this. These are sort of basic methods. Okay. Then there are a lot of functions to create graphs of prescribed type. So for example, during the first video, I was talking to you about complete graphs or bipartite graphs. And you can see, for instance, you can create a full graph here. You can create a full bipartite graph, etc. I don't know why my mouse is acting up. Okay, never mind. So you can make a graph, bipartite communities. I mean, you see all of those. This is mostly for deterministic graphs. And there's a whole bunch of methods for creating random graphs also, because these are very, very important in applications, and we'll be seeing some of those. So you can see it's typically, if a name starts with sample underscore something, it means you're creating a random graph, whereas if it's a make, it's just a regular graph, in the sense of it's a prescribed type of graph. So these are all sorts of graphs that you can see here. There is, I'll show you some examples of that in a second, etc. And finally, there's also something that is quite important. There's a function called the read graph that will import graphs described by other programs, graph analysis programs. And so, for instance, I'm mentioning Pajek because this is something you might run into. I actually don't know exactly what is happening to Pajek these days. I haven't checked in several years. This was, at least before, a Windows program that made it very easy to do graph analysis. There's a language that I might give you a few notions of, which is called the dot language, which creates graphs as well. It's very useful if you want to do presentations and the like. So these are graph descriptions that you could load using that function read graph. Now, let me show you a couple of examples. As I said, that's not the main point here is to show you how to do a few basic things. We'll go into much more detail later. So the first thing I want to do is, if you remember at some point in the video, I wrote a graph near the end of the first lecture on graphs. I wrote down a graph and I extracted its adjacency matrix. So let's go the other way. Let me make that adjacency matrix that we ended up with, and let's create a graph from that adjacency matrix. So I have a matrix. I just say that I'm going to create a graph from adjacency matrix, and I store this in the object G. I'm going to show you what G looks like if you just plot it like this, and not plot it, display it like this, and then what happens when you plot. So what we have is an igraph object. It has 3 vertices and 3 edges, and it's saying, so in igraph, most things are called edges, regardless of whether they are arcs or edges, but you can work with oriented, so directed or non-directed graphs, okay? And then finally, plotting the graph gives me this. So if you turn back to the end of that video, you will see that this is essentially the graph we have. There's a two-way connection. So the only thing when you're plotting like this, it is showing, if you have an arrow in both directions, it's showing just one arrow, but with 2 endpoints here. So there's a two-way connection. There's an arrow in each direction between 1 and 2, and there's an arrow from 2 to 3. Okay, which is exactly what this says. I can go from 1 to 2, from 2 to 1 and to 3, and from 3 I can go nowhere. Okay, so this is the graph. Let me show you an example of, we talked briefly about bipartite graphs. This is a very well-known bipartite graph. So here, what this function does is it creates a full, so complete bipartite graph with 3 vertices in one of the sets and 2 vertices in the other. And when you look at this, so the 3 first vertices will be 1, 2, and 3, and you can see that 1, 2, and 3 connect to 4 and 5, but not to each other. And the same way, 4 and 5, which could compose the second set of vertices, 4 and 5 connect to 2, 3, and 1, but not to each other. Okay, this is a non-directed graph. I can specify that the graph should be directed. So by default, the graphs are not directed most of the time. except if it's a function that creates a graph that's automatically directed, because there are graph specifications that say that graph is directed, but unless it's that way, it will create an undirected graph unless you say that you want it to be directed. Okay, so here I'll make the same graph, but I am using a directed graph, and so what you can see now, it's put arrows in both directions, but the same way as before, vertices in 1, 2, and 3 connect to vertices 4 and 5, and there is no connection between vertices in the individual subsets of vertices. Okay, so this is K32. It's a graph we'll see from time to time, whether in this undirected form or in the directed form. Let me show you Platonic solids. So you probably don't know these, but I mean, these are well-known solids, and you can, for example, here I'm making 1, 2, 3, 4. This is a dodecahedron. So it's a graph, and I mean, it's meant to represent a physical object with 20 faces, 20 vertices. I can make all sorts of things. So a tetrahedron, or for example, cubical would be the one that's, of course, it's a cube. Okay, and these are what are called Platonic solids. They're a sort of bunch of well-known objects in geometry. So these are some of the graphs that are predefined, and to make one of those graphs, you would just say make graph. And what I've done there, by the way, so you can see that I've made them into a list, and I can then address specific graphs by giving their position in the list. This here, I'm going to use now a random graph. So this is a graph, it's called a small world network. You might have heard about it. It was very, very popular quite a few years, well, no, 10, 15 years back. The idea being that there are vertices that are highly connected to others, and others that are a bit everywhere, but the distance between vertices is not very large. We'll come back to that. Okay, so for now, I'm just going to show you how you generate this. So here I'm going to make 100 vertices graph and plot it. You can see how things are going. If I take a larger, that's the neighborhood. So this is another graph. There are properties to these graphs. We'll see some of them in person later. But for now, this is this. Another type of graph that's very popular in applications is what's called a scale-free network. So here, for example, I'm showing you that you can make relatively big graphs. So number of nodes is the number of vertices. Number of edges is the number of edges. And these are, again, parameters. And here, I'm not going to plot the graph itself because it's going to be too massive. It's going to take a long while to do this. Instead of that, I'm going to show you the degree distribution. So remember, we talked about the degree. We'll come back to using degrees and etc. But for now, just let's plot this. So this is showing you with a scale-free network the type of degree distribution that you get. Okay, so this is the frequency in so this is in log scale. Okay, both x and y are log, and this shows you the degree distribution. So that's the frequency of vertices that have the given degree. So the degree 1, there's 1 plus 0 here, so we are just below, okay, because it goes down quickly. And then this is a characteristic of scale-free network. It's essentially, Actually, if I did log, let me see if I do log y. Oops. Do log y. Yes, so it's essentially a straight line if you're plotting in the x and log y coordinates. I don't know what's wrong with my mouse. This is interesting. Okay, I can't, well, it's not my mouse, it's actually my keyboard. My keyboard is acting up. Okay, and okay, now we've made a few graphs, I mean random graphs or not random. Let me show you, so I'll take an example. It's a well-known graph. It's called an Erdős-Rényi graph. It's got 50 vertices and 100 arcs. We'll come back to that graph again later, but I'm going to do it in a way where I'm allowing directions and I'm allowing loops. And this is not okay. Okay, so I don't know why my keyboard is refusing to work. So you can see I've made a graph with 50 vertices. This graph, and let me show you things you can do with it. So for example, remember the order of a graph is the number of vertices. Here I know it's going to be 50, but suppose you import a graph from the internet. You don't necessarily know what the order is. Well, you can run it. G-order, graph order, gives you the order of your graph. If you want to get the adjacency matrix, you're going to get some information like this. And so just note here that the adjacency matrix is what's called a sparse matrix. So this is very convenient because sparse matrices, the only information that you keep are the non-zero entries. So here it's showing dots, but this is actually empty. And the sparse matrix just says there is a connection from one to this one. I don't know what index that is, but so it's a much more compact way of storing a matrix. You can also get it to export in different formats. Again, look up the help on other adjacency matrix and you'll see what you can do. Other things that we can do is look for connected components. So connected components you'd get by looking at G, components of G. And here, this is something we haven't seen yet, but this is a directed graph. So when I'm looking for components, there's something called strong components as compared to weak components. So here I'm looking for strong components. We'll come back to that. And I'm just saying what I'm going to do here is I'm going to color the vertices in the graph as a function of what component they belong to. And so here, this is what I'm doing. This is going to be different. Oh, gosh, okay, run. So here it's extracted the connected components and it's labeled them using different colors. So this is the same graph as before, except that all the vertices in the same color in a group like this, for example, are members of the same, it's called a strong component, the same component. So I have access from any of those vertices to any other of the vertices. We can test some properties of the graph. So for example, is it a directed graph? Is it connected? So globally, is there one single connected component? Is it bipartite, simple? Are there multiple arrows? Are there any loops? And you could run, wow, you can run this and you get an answer for, so for a loop, for instance, it's answering for each vertex, and you can see that some vertices are loops. That means there's an arrow from themselves to themselves, and all the others are not. This is a directed graph. It's not connected because there are more than one connected component. It's not bipartite. It's not simple. And here, let me do the same, but without the direction. And here, when I plot this, there's a lot the components are much larger because this is the direction of the arrows does not count. And if I'm looking at this, you'll see that one thing that is different is that a graph is indeed simple. If you recall the definition of simple, it was that it was a non-directed graph. There were no self-loops, connection of a vertex with itself. It was one graph, etc. So this is satisfied by this graph. And this is it for the beginning of how to use igraph.